So now it turns out in practice, you can also make simple band gaps without using op amps. So let's sort of briefly see how you might do that also. So I'll copy the old one. Let's say I'll take this one. This is our old circuit. So first let's try to understand. Oops, sorry. Yeah, I'll just not show everything. I'll just remove these things. And let's say we do something here. Okay. Yeah. This is our first variant of bandgap. Let's look at this. Okay. So now tell me, the op amp is essentially this first stage and second stage. So what is the point of having a high gain here in the first stage? What is it trying to do? It is trying to make these two node voltages to be equal. And what are these two PMOS transistors trying to do? Loading effect, but in the circuit finally, what are their role finally? It is trying to make the currents in the two branches equal. So finally in words, the functionality of the op amp in this circuit seems to be to keep these two voltages equal and the branch currents here to be equal. So which means if I can accomplish the same task without using an op amp, I'm okay. Right? So let's see if we can even do that. And for that, I'll consider a generic. Okay, let me erase this. Let's see. Yeah. Yeah. So all I have to do is to try to keep these two voltages here and make sure the currents here are same, right? So let's, before even going to this thing, let's consider general structure. Let's say I have two things here. My goal is to, let me draw it neatly. My goal is to enforce equal currents in the two branches and make sure the two node voltages are equal, right? Now let us say I want to have equal currents in the two branches. What is one simple thing that you can do? If I want to have equal currents in two branches, what can we do? I mean, let's say you have some current flowing here. I want to copy the current and put it here. What do? Current mirror. So all I have to do is this. I have to have this fellow. Now I just have to make sure that I obtain the required gate voltage by connecting it like this. This will ensure that I generate a gate voltage so that it provides the required current. And to copy this current to the other branch, I just have an identical PMOS transistor mirroring it. Again, let's start with assuming ignoring all channel length modulation, all sorts of things, right? Now if I do that, the currents in the two branches are equal, but what can you say about the two node voltages? Will they be equal? They need not be, right? This is set by the gate voltage, this is the drain voltage. They will not be equal. So which means I can't connect directly like this. So let me just keep it. Now tell me, I want to have these two nodes to be equal. Let us say I have some voltage VB. In principle, I can try to go and connect like this, but of course that will load this voltage, blah blah blah. If I don't want this to be loaded, what can you do? Common source or something else? I don't want this to be loaded by this anything I connect here. What should I do? I put a buffer. Buffer is common drain. So all I'll do is this. I'll have this VB. I apply VB at the gate. So it's buffered at the source and fed here. So I'll have the same NMOS transistor here. Right. So now it should be clear that the two voltages are equal. So this is doing one half of the job. This is doing another half of the job. Now let us say I want to keep the currents in this to be equal. What do? Yeah, I can essentially But now look at the circuit here. Here, of course, I can connect any gate voltage in principle so that things are in saturation. But look at the circuit. I have a PMOS transistor. Gate is connected to something, source is connected to something. It is acting like a current source. Same is the case with this NMOS transistor. So you have two current sources acting independently. So what do you foresee? This might not be defined. So which means I should have some kind of negative feedback to set it. Now let's, my goal is to keep the currents in PMOS and NMOS transistor to be equal. Is it okay? So let us say, now we can see it easily. If let us say the PMOS current is greater than the NMOS current, what can you say about this voltage? That will start increasing. Fine. Now if the PMOS current is greater than the NMOS current, what should I do to correct for this now? Increase? Yeah, or I should actually increase the current in the NMOS transistor. Right? So if I want to increase the current in the NMOS transistor, I should essentially go and increase the gate voltage VB. So what do you suggest we can do now? I can diode connect to the NMOS transistor. Again, this works well as long as there is no channel length modulation. In presence of it, this just won't work as nicely, but yeah, it's okay. Okay, so now we know how to accomplish this task of keeping the two node voltages to be equal while ensuring the currents to be equal. So which means I can just now replace it here. Now, do you think is there a unique way in which I can connect this circuit here, or there are multiple ways in which I can connect? I mean, I have this structure. In principle, I can go and connect it here. Now, my question is there a unique way in which I can connect these two nodes here, or is there a couple of ways? Huh? Okay, maybe I'm overcomplicating. Huh? Okay, or I mean, remember here I can either have the 1x diode, NX diode, or I can have this way. There are two possible ways. That's what I was trying to get at. Right? So let's see what is the what is better and what is not. So first let's consider, okay, I'll redraw this here. So what I have done is I'm having now an NMOS transistor here. The job of the NMOS transistor is to keep the currents, the voltages to be equal, and this is self biased this way. And then I have the PMOS transistor here. The job of the PMOS transistors is to keep the currents in the two branches to be equal. Right? So this is one way, or I can essentially interchange these two. Right? Let's see what is the pro and con, or what might be the downsides or upsides for the two cases. Now tell me, is there a feedback happening here in the circuit? Is there a feedback here you see, or you don't see a feedback? There is a feedback. So let's see what kind of feedback we have. Or maybe actually I'll take the other side. What I'll do is I'll flip the connection for now. Hold on. I'll consider this case for now. Okay, so now let's look at what kind of feedback we have. Let us say I go and increase this voltage. What will happen to the drain voltage? That will decrease. So the drain voltage drops, so the gate voltage drops. So what can you say about this voltage now? So what kind of feedback we have? Oh, we have positive feedback. But let's not get alarmed so much. Let's calculate and see what is the loop gain we have for the positive feedback. Okay, so tell me this. Let us say this has a slight incremental voltage V test. Ignore R naught of all transistors to start with. What will be the current flowing in this branch? Let me erase all this. The gate voltage is Vt. What can you say about the current here? Huh? That's very approximately, but okay. For small signals, what can you say about the diode? It's an effective resistance. So I'll consider this to be Rd, some Rd by N. Let's make it very easy so that it's apparently clear. So this is a resistor with a value Rd. This is a resistor with a value Rd by N. Now I apply input at the gate. At the source, I have an effective resistance of R1 plus Rd by N. What is the drain current? Yeah, how did you say that? Yeah, what is this voltage now? I mean, approximately Vt, but slightly more realistic so that we can. Gm times the resistor by 1 plus Gm times the resistor, correct? So which means the current flowing will be this voltage by the resistor value. So that I'll directly write. So this current is going to be Gm of the NMOS by 1 plus Gm of the NMOS times R1 plus Rd by N times Vtest. Is that okay? Again, we are all doing small signal calculations. So if this is the current flowing in this branch, what can you say about the current flowing in this branch? They should be same. So that is also same. So Gmn Vtest by 1 plus Gmn times R1 plus Rd by N. So then what can you say about the return voltage here? I mean, this current is flowing through an effective impedance here. What is the R equivalent of the structure? Remember, I have gate and drain connected. Now this is like a two terminal element. This sort of bilateral. So this can be replaced with a resistor of 1 by Gm. 1 by Gm plus Rd. Is that okay? So if I look at my loop gain, so the return voltage I get is Gmn by 1 plus Gmn R1 plus Rd by N times 1 by Gmn plus Rd. Is that okay? Now, if the diode is sufficiently forward biased, what can you say about the on resistance of the diode? It's going to be very small. So let's ignore Rd. So this becomes essentially, so I am ignoring Rd. So Gm cancels. I'll end up with 1 by 1 plus. Is that okay? This is your loop gain. Now, do you think this is greater than 1 or less than 1 or equal to 1? It's definitely less than 1. So which means I have a positive feedback loop, but the strength of the loop gain is less than 1. Is that a matter to worry or not to worry? Not to worry. Why? Yeah, I mean, the feedback is very weak. So essentially, right? See, remember, it's not. If you have positive feedback, let us say the loop gain is K. Let us say apply some Vi. What will happen first? Let's say the output is 0. So my output will first become K times Vi. Correct? Then what will happen? K times Vi is fed back. So that will get K square Vi. And this will kind of keep happening. And this will all happen instantaneously. Right? So we'll have an infinite geometric series. And when will this converge? So as long as you have a positive feedback loop gain to be less than 1, you are safe. So if I make this connection this way, you are fine. But let's also see what will happen if I flip the connection, because if in the other case the loop gain is much smaller than this, that is even better. Smaller the loop gain of your positive feedback loop, the better it is. So let's quickly see that. I didn't copy this. Okay, fine. Okay, so which means if I flip the connection, what happens is this: the resistor here, that will be R1 plus RD by N. You can write it directly, you don't have to recalculate fully. This is RD, right? Thus the impedances on the two sides have changed. Earlier I had R1 plus RD by N here, RD here. Now I have flipped it. Okay, we can directly write it now. So what is the current now? What will change here? Instead of R1, I'll have just RD. Okay. So which means here also instead of this thing, I just have GMN times RD. So what is the impedance now of this structure? 1 by GM plus. So I am just replacing directly here instead of RD I have. So once again, if I ignore the diode on resistance, assuming it to be sufficiently forward biased, so what does it simplify to? Let's ignore RD, let's put RD to be 0. So this term goes off. I have GMN times 1 by GMN plus R1. This is essentially 1 plus. So this is guaranteed to be greater than 0. Sorry, greater than 1. So flipping it this way is not a great thing to do. So now which means it is sort of well established that the connection should be this way. So let's see if I can. Okay, I didn't copy the circuit. So here I have the single diode. Here I have the N diodes. So this is what you should have. And if I do this, whatever that was happening when you had op amp, the same thing is going to happen. You can construct the bandgap reference this way. So this is sometimes called the self-biased bandgap reference. And before we conclude, just one point. See here, we sort of established that if I interchange these two impedances, the loop gain of the positive feedback loop is greater than 1, right? And this is the correct configuration to have. Now look at the circuit and tell me, besides the positive feedback loop you have here, is there some other feedback that you can identify? Some negative feedback? Which one? This one? Yeah, I see pointing out. This is sort of, remember this is a source regeneration, right? Here there is inherent negative feedback. So the way you can argue is this: although I have positive feedback, there is also a strong negative feedback here that is sort of reducing the loop gain of your positive feedback. Okay. Whereas if I flip the connection, right, which means what will happen is this: if I flip the connection, okay, let me see if I can quickly draw. If I flip the connection, here I have one diode, here I have N diode and R. Now you see that the source regeneration is provided by this diode resistor only, and that, as you know, is pretty small. It is as though there is no negative feedback, right? So that is why here is the correct configuration to use. So although we have a strong positive feedback loop here, we have an even dominant negative feedback loop because of the source regeneration, which kind of ensures that the loop gain of your positive feedback loop is reduced and it's less than 1. And that is also very apparent if you look at the loop gain expression. Yeah, here we had 1 by 1 plus GM R1. This is your negative feedback thing, right? The source regeneration. If this is the loop gain of the negative feedback loop, if this is sufficiently greater than 1, that also helps in suppressing the positive feedback loop gain. So that's one way to quickly remember what is the correct connection. That is the resistor you have for the source regeneration, that should be the maximum one here. If you have two impedances, you put the higher impedance on the source side, that degenerates your GM. Yeah. Okay, cool. We'll stop here and we can continue. Yeah.